In the next section, we'll study some formal models for what computation with randomness could mean. And I just want to set the stage solidly for talking about what running time here is. And you'll see it's not actually a problem in the end, but to capture the full possibility of what could happen, I think is useful to start general. As before, we'll think of a minimalistic model of computation, Turing machines again. The formal definition was in Unit 2, if you want to look up the details. Here we add a little bit to this Turing machine. So again, Turing machine, it has some states. It has an input alphabet, which is the initial things written on the input tape. A superset of that is the set of all symbols I can write on the tape. Then I have the transition function. That's the program, the most important bit. I have an initial state. I have some blank symbols that the tape is filled with if I haven't touched it yet. And I have a specific state where I terminate if I ever reach this. Now, a probabilistic Turing machine is that same thing, and it's a deterministic Turing machine, which maybe is worth stressing, where we additionally have another read-only tape, which is conceptually filled with random bits. So it's an additional tape. So the machine has two heads. We've talked about multi-tape Turing machines very briefly in Unit 2, or at least it's on the slides. In general, you can define Turing machines with several tapes, and you can show that you can simulate everything on one tape with a bit of a blow-up in space, blow-up in time, I guess, and space, but time is more affected. So here again, we do the same. So think of your Turing machine with the states here. There's the infinite tape for the input. Oh, this keeps... Oh. There's some weird operation I do, and then it loses focus in the window and doesn't come back until I'm on the keyboard. So that's the input and output tape, which you can read and write. And then there's the random tape. Where you can still move your head back and forth, but you can only read. There's no writing facility. Now, I guess you can imagine how this would be formally defined. The key thing that changes is the transition function. The input now is not just a state currently of the current position, and so I didn't finish drawing the read-write heads, I guess. So there's the read-write head here. I can move left and right. And there's the random bit read-write head. But this can only read things. So it's not a read-write head, it's just a read head. So the transition function, what the machine can do is it can take this symbol and it can take the symbol on the random tape as an input. Previously, it only had the state and the symbol on the tape. Now we have an additional symbol, random bit, R. And the next state, as before, is a new state for the internal memory. It's a new tape symbol I write on the input-output tape. Could be the same as A. It's a head movement for the input-output tape and a head movement on the random tape, but no written symbol because it's a read-only tape. Okay. So far, so good. In particular, the whole machine is supposed to be deterministic. Once you fix the random bits, there's nothing further random. All the randomness or all the non-determinism comes from those random bits. If you fix what's in the red tape, then the rest is determined. We'll eventually get to the point that we say this tape is filled with random coin flips or bits that are chosen from this Bernoulli 1/2 distribution. And there's your IID, mutually independent, all identically distributed. So to define what computation is, we go through the same steps as in Unit 2, but I compressed them a lot. Back then, we had the configuration of a Turing machine, which was just a concise way to write what's on the tape and what the current state of the machine is, and where the tape head is, and that's all we needed to know. So the compressed way to store that was this alpha q beta, where your tape symbol contains alpha beta concatenated. Q is your state, and the position of Q within alpha beta indicated where the head is. And if I remember correctly, it was on the first symbol of beta. Okay. Now we have a second tape, so we have a second component in the configuration. It's just a pair of those things. And the second component works exactly the same, except that now these rho and sigma together are the content of this, the red tape, of the random bit tape. Okay. Then we can define this computation relation, or it really is a function here because it's deterministic, in almost the same way as we had back then. You follow the transition function. The configuration uniquely determines the state you're in, what you read as symbols. So you know what the output will be. Then you replace the state with the new state. You move the heads if needed. And maybe you replace a symbol here if you write a new symbol, just as we had it back then. And based on that, we can define what is the function computed by a Turing machine. And so the difference here is that the actual input is just some string x, and we have some random bits to somehow decide. And for now, let's say if we fix the random bits rho as part of the input, I can write m of x and rho, the random bits are given, is a certain value y, exactly when from the initial configuration, I can reach the terminating condition where I reach this halting state, and I've produced y on the input-output tape. This is almost the same as before, except that I have the second component, but for the function computed, I'm kind of ignoring it. I just say there's something will happen to the random bits, but I don't actually care. These are just defining what the steps in between are. But this is deterministic, okay? Important. If I fix the random bits rho, everything is predetermined, and the machine, depending on how it's programmed, either it can reach a halting state or it may not. It might be broken, but this will be one well-defined sequence of steps. And if it reaches some configuration, it reaches uniquely only this one. And so y is well-defined. It's either not terminating, then there's no value, or it's a single value. Okay, many words for saying deterministic. Of course, now we don't want to fix the random bits. They're not part of the input. These are randomized machines. So the randomized computation will become a random variable. I'm essentially now taking this function m computed by the machine. I keep the input, but rho is now formed by random variables, namely by these IID Bernoulli 1/2 random variables. Okay. And so now this computation, or this function computed by the Turing machine, has become a random variable. And we can talk about probabilities for computations. For example, the probability that the machine computes a certain output y is the probability over well, all the bits that make it output y. So far, so good. In principle, now a randomized Turing machine could have different outputs, right? It doesn't need to compute the same value y. It could compute different values y, and it could also sometimes not terminate. Of course, from a programmer's perspective, what we really want is a machine that outputs the right thing with at least a good probability, but we'll come back to that a bit later. For the moment, this I think is very natural, but there's a big caveat here in that there was a lot of cheating involved in all those definitions. And the first cheat the cheat becomes obvious at this point down here, where I said we put in these random variables, and sometimes the machine doesn't terminate, which means it might need an infinite amount of random variables. So how am I even going to write down the configuration? So all of this is getting a bit more tricky, just because of this possibility that the machine keeps asking for more bits. But then why would it do that? Like, can't we just restrict it to cases where we never use infinitely many random bits? Why would you? It sounds completely stupid. In particular, we had this in Unit 2 as well. We said in general, Turing machines, if you give me some arbitrary program, they might do all sorts of nonsense. But for the discussion of P versus NP and all that, we restrict to total machines that always terminate after a fixed amount of time. And you can always convert. If a machine would be running for longer, you keep a timer, and when its time is up, you just shut it down. Now, for randomized Turing machines, for probabilistic Turing machines, there are some simple tasks that seem not to work with that, and so we don't want to disallow these infinite computations. And here's a simple example. Again, I'm sure people will have seen random rejection sampling, but let me go through this slowly, and you'll revisit it in the tutorials just to make extra sure. So the way we define things is everything that we have that is random are random bits, and they are uniformly random bits. Now, suppose we want to simulate a six-sided die, a uniform six-sided die. How can we do that? I mean, I could start with, okay, I'm flipping one bit and ask, is the number odd or even? And then I've nicely divided things up. So I have three options left. Is it, say, if it's odd, is this 1, 3, or 5? How do I do that with just bits? Seems tricky, but luckily there's a general solution that always works and is a lovely algorithm, which is called rejection sampling. So for this concrete example, it's spelled out here. I just called it roll die. The function will refer back to that a few times. It keeps looping in, it does this as a potentially infinite loop. You draw 3 random bits. That gives you 8 possible answers. You take this as a representation of a number between 0 and 7. And then if it's out of bounds, the die should have a number between 1 and 6. If it's out of bounds, which means here it's 0 or 7, then you discard this, you reject that random outcome, and you just try again. Whereas if it is between 1 and 6, then you output that number. Okay? Have you seen this before? Rejection sampling as an idea? It's a general trick. If you have something that's hard to sample from, you sample from a superset and then check, have you hit the set you wanted to sample from? And if not, you just try again. And the beauty of it is that it is very easy to show that it is perfectly uniform. Whenever you return something, it has to be perfectly uniform because you gave all the outcomes 1 to 6 exactly the same probability, namely 1 out of 8. Now, the downside, of course, is it might never terminate if you're constantly unlucky. If your random bits are always 0, then this algorithm never returns. Now, of course, you also know, if you've seen rejection sampling, if you do this in practice, it never causes problems, at least in this algorithm, because the expected running time is constant. And so to prove that, you can compute what is the probability of doing another iteration of the loop. And here, the probability to leave the loop is 6 out of 8 options. So in 75% of the cases, we're done after 1 iteration. And in 75% of the remaining 25 cases, we're done after 2 iterations. And so you see where this is going. So the number of iterations, I didn't put this on the slide for some reason, is a geometric distribution. And the number of, so success means 3/4. That is, I'm doing exactly the same as if I was flipping a biased coin, where with probability 75%, I'm immediately successful. And otherwise, I keep trying and I count how many tries did I need. So that's exactly the geometric definition, geometric distribution by definition. And then you could either look up, we know the expected, this is annoying. The expected value, the expected value of the geometric distribution is just 1/p. That's worth keeping in mind, but of course you can prove it using the series that is on the slide. Sorry, P, here it's 1/p. And the proof is just this sum. That's by definition that's the definition of the expected value. So this algorithm is correct. It uniformly samples. Its running time is a bit wonky. It sometimes takes longer and sometimes takes shorter. But it's well characterized. We can understand how long it takes. It's a random variable that's well understood. And it has a small expectation. So after a constant amount of time or constant amount of iterations, you'll have your output. So why did we talk about this? I mean, number one, it's a beautiful algorithm worth knowing. Rejection sampling is a beautiful idea. But it also shows you if you were to try this sampling in a different way without this kind of infinite loop, it seems really hard to do. And so we seem to want to deal with infinite runs in this context. Question? So the question is, can you use arithmetic coding for this? I think you'll end up with the same problem. Yeah, think about it. I mean, you could essentially turn, if you want to sample from a more complicated distribution, or maybe even a sequence of things, then arithmetic coding is a good way to turn to generate a sampler that is efficient in terms of the number of bits that it uses, but you can't avoid this case that you have to keep going with arithmetic coding. The nice thing is you'll prove in the tutorials that it's not possible. So it's not a hard proof if you look at it from the right way. For here, I'll just leave it with the statement that we seem to want to keep infinitely running or potentially infinitely running probabilistic Turing machines because they have practical use cases. Again, you'll look at this a bit more in detail in the tutorials, and this is only one example. So what does that mean for our definitions? What could possibly go wrong, right? Number one, if you have a randomized Turing machine, it could still do the same nonsense as before. You could enter an infinite loop, even if that doesn't consume more random bits. Okay, but that type of problem we can actually discuss away. That's the same as before, and we can keep a counter, or there's ways to deal with this. But there's a new problem that didn't occur before, which is what we used in this roll die. We have branches in the code, and these are based on random bits. And there is a possibility to be constantly unlucky. Like in the case of roll die, always take zeros. So formally, you could say for every time t that you put your timer on, there's a certain probability, non-zero, that you need more than that many steps. And the computation is doing something sensible there. It's a new thing that didn't happen for deterministic Turing machines before. It did happen, though, for non-deterministic Turing machines. And the formal definition there is just said, okay, the running time then is infinite. If there's an option non-deterministically to keep going forever, then that should be infinite time. Okay, so we'll probably have to keep that. But now, like for our algorithm roll die, is that a problem or isn't it? And also, can we define the expected running time here? Like it seems the expected number of loops was not a problem, but can we define properly what the expected running time of our Turing machine model is in the presence of these weird cases where it keeps running forever? Well, the answer is of course yes, but that's the reason why I introduced some of the abstract probability spaces terminology. You can properly define it, and here's one way to do it. The key question is what probability space do we need? It seems if you start with random bits and everything's finite, oh, everything's lovely discrete. Yeah, but if things are infinitely long, not so quick. So if you had finite bit strings, then that's discrete, even if they're infinitely many. What we really need here is an omega language, I mean, I wrote this here, or I'll write this here in the way formal language people would write it. 0, 1 to the omega means it's technically as a function that maps the natural numbers to 0, 1s. That's one string. If you if you think about finite strings, you could say a finite string is what? Well, it's mapping the numbers 0 up to some number to elements in the alphabet. That's a string. And so the generalization is, well, I'm doing the same, but it's an infinite domain. I'm mapping all of the natural numbers to a bit. That's an omega word. So this 1b is called an omega word. Okay, I have to be a bit clearer. That's omega and that's w. And then I can talk about these in the same way. And you can talk about regular omega languages in the same way you do regular expressions for finite languages. There's some cute automata theory in there, but we won't need that. You could also think of these as infinite, as real numbers between 0 and 1, written as infinite binary fractions. So in particular, this is actually a bijection. You can take your infinite omega word and just write 0 dot and then the digits, the bits. And that's a number between 0 and 1. And you can exactly represent all real numbers that way. Okay. It's kind of almost by definition, so maybe it's not super exciting. Bijection? I'm not sure. Like maybe the problem is there's potentially several representations for the same real number. 0.011111 is the same as 0.10 100. So maybe take this. I don't want to lie. So maybe bijection is pushing it too far. Because these are, as real numbers, these are the same. But as omega strings, they're different. Cool. So maybe that's the reason why we don't directly go to real numbers. As a computation, these might trigger different computations. They're different bits. Okay, so morally, you can think about them as kind of real numbers, but just the representations as infinite representations. Clearly, you see that it's a continuum, right? These are at least as big as the real numbers between 0 and 1. So you can't, they're certainly not discrete, but they might be a bit bigger. So also for our configuration of the Turing machines, formally, let's just write that the sigma here, so the remaining part, the right part on the infinite tape, let's say that's an omega word. So we're on the safe side. If the machine needs more bits, there's always going to be more bits because it's infinite. It's a bit annoying that we can't write down a configuration anymore because it's infinitely big. But let's ignore that. It's not a big problem, really. We don't write them down. What we need now is a proper probability space for these infinite bit strings, because that's what we want to take expectations over and compute probabilities from. And it turns out that's a known thing. It's known as the Bernoulli probability space. And as for the Borel sigma algebra for real numbers, where you had open intervals as the kind of minimal elements, here you have, I don't know, they're sometimes called cylinder sets, but I guess it's just a prefix. So the pi x are just all the infinite 0, 1 strings that start with a certain prefix x. You can think of it as kind of a restricted way to represent intervals in the real numbers. For real number intervals, you can have an arbitrary start and end point. These numbers here are, in a way, always dyadic intervals. They start at a negative power of 2 and have a length negative power of 2. Right? If you say this set is all the real numbers, it corresponds to real numbers between 0x 0x1 up to whatever xn, and then zeros all the way up to 0, then the same x's, and then all ones. Right? Formally, pi x is just a set of omega strings. And it's all those omega strings that start with a given finite prefix. So important here is that, I should have made that in red. The prefix has to be a finite prefix. And it turns out you can turn this into a sigma algebra by taking the closure under these operations. So you take all those pi x sets, and you take countable unions and complements, and that is a well-defined sigma algebra, the Bernoulli sigma algebra. So that's the measurable sets we can talk about. Okay? These pi x's, unions, and complements thereof. And what's the probability? You can assign the measure of 1 pi x. And it's very natural, I think, that you say, if we've seen a certain prefix of a certain length, I've seen n random bits, so it should be 2 to the minus n as the probability to see exactly that string. And the rest is, I don't know what comes after. I'm summing over all of them. And so you only fix the probability, it only fixes the prefix. So this defines the probability for the generators. And the probability for any other set you can derive from that and using the abstract properties. And you'll do that in the tutorials to practice it. Okay. Maybe let me briefly sketch how this could look like. If you go back to our roll die example, what are the kind of bit strings where it terminates? It always chooses 3 bits at a time. And all of these, as I'm drawing here, are numbers between 1 and 6. That's 6, right? Yeah. So in all of these cases, we're done. In these 2 cases, we continue. So you have to zoom in here. Then you do the same 8 cases. So we have 0, 0, 0, and then 0, 0, 0, 0, 0, 0, 1, 1, 1, and all the other options, 0, 1, 1, etc. Here we terminate again. For these 2, we have to continue. And this, of course, gives you some large tree. Um, what's the probability that this guy terminates? Well, it's the measure of all, it's P of, I guess I want to, can I sum here? I guess it technically is closer to an integral. Let's integrate over all rho. Do I have a, yeah, 0, 1 omega, I guess is the closest. Oh, not again. This is some super annoying. This one's also frozen, so that's not a good sign. Well, you would want to go over all these infinites, the omega words rho where the algorithm terminates, and sum up their measure. I lost some of the drawings, but I guess we'll have to keep the good memories of them. Let me not repeat the drawings, maybe. The point was you can define a language of omega strings. So the roll die example. The roll die terminates if and only if the initial bit string we start with is in some language T, which is a subset of these omega languages. And we can now, with this Bernoulli probability space, we can talk about what's the measure of that set T. And you can re-express that using these prefixes. And the prefixes nicely turn into the cases where the algorithm terminates. I think this is doable enough, but it's worth that you do it actively in the tutorials, just to kind of be forced to mess around with the definitions a little bit. We won't much use that formal, like this probability space and how to work with it. We won't need it much, but I think I always felt it was very unsatisfying that you talk about these randomized algorithms, and technically many things were not well defined. The expectations, you always needed hand-wavy bits to define what they mean. So with this setup, which is not too complicated to work with, as you'll see, you can do this properly. And the benefit is, for the probabilistic Turing machines, we can pretend that there's no randomness. The randomness is upfront. You decide once for this infinite omega word of bits, and then the machine can be deterministic, and everything can be computed based on that. The last bit for this to finish off is generalize what is running time for our new notion of Turing machines. And we can define the worst case time as before. So the time the machine takes on a given input is the supremum of the time steps over all computations. The original Unit 2 slides had an infimum there, which is nonsense. It has to be the worst case, so it's the largest. And it's supremum instead of maximum because it could be infinity. It could be infinity at the time. But we had the very same definition for non-deterministic Turing machines. There it was also possible that some branches of the possible computations just keep running forever. So time without a qualifier is the worst case time on that input. Right? Time is worst case. And that's not always very helpful. For the roll die problem, it would be infinite. Right? So time roll die on any input. It doesn't have an input actually, right? It's just spitting out some random. It would be infinite. Oh, not again. I don't know what this is. It needs to be solved. This is super annoying. It happens way too often. It's new nonsense. Yeah, have an idea. Maybe not now. Okay, so here the worst case time is infinite. But we can define an expected time now that we have a probability space at hand, and that's just the expected value of this. And here's a last bit of notation we'll sometimes use. I write in the subscript of the expected value operator the random thing that we take the expectation over. This doesn't technically add anything. It's just for clarity of the presentation. This is stressing that the random thing we're talking about here is the random bits. Everything else is deterministic. And then formally, you can say the expected time, what we take expectation over is the smallest number of time steps t that it takes from the initial configuration to reach the halting configuration. If you start on a specific random row, that's the random bit. Okay? In red, this is the random part. And then, of course, also the t is a random thing because it depends on row. So the whole thing is the whole infimum is random. The shortest number of steps to reach the halting state for a specific sequence of bits. And the expectation over all the bits, that gives you the expected running time of this probabilistic Turing machine. As before, we define instead of a specific input, an input size, you just take the worst case of all inputs of that size. That's as before. So I try to be consistent with having lowercase time to be on a specific input and uppercase time, the worst case over inputs of a given size. Of course, instead of the expectation, you could also take the full distribution, and sometimes we will. But what's useful here for starters is the expected time is finite if and only if the probability to never terminate is 0 exactly. In other words, we almost surely terminate if the expectation is finite. And that's pretty much what a sensible algorithm should do. It's okay if there is a hypothetical option for it to run forever, as long as it actually never does so with any positive probability. You will remember from probability theory that this almost surely, something that happens with probability 1 is not so intuitive. You can upfront fix some event that had probability 0, but it can still happen. In hindsight, you know. But we won't see it happen for our roll die algorithm. Just for the notation, I mean, for the formal definition is not so important. Instead of time, you could also look at how many random bits did you need. That might be a useful thing to look at. You can formally define it by how far into the infinite row did you ever move. And here's a way to formalize that. But the intuition is just how many random bits did you use. Again, you can define this as the worst possible. Again, if you fix just the actual input, it's a random thing. So it's the random number of random bits that you used. And the small case random is the worst overall possible random bit strings. Again, could be infinite. So oftentimes we'll talk about the expected number of random bits that we used. And that's a bit of a mind twist, that the cost of random bits is also random, but it's not such a bad thing if you think about it. I mean, it's not so unintuitive. You just consume this special operation, bit ein Bit, give me another bit, a certain number of times, and how often might depend on the previous bits. Nothing more surprising than for the running time. But we'll use this occasionally, For some algorithms, it's important to economize on the random bits as well.